Hi, I'm going to present you today some of the work that we've been doing on mostly focused on specimen preparation and some examples of atom probe tomography experiments on chemical fixation and maybe cryo-fixation for nanoparticles analysis. So this work has been pushed mostly by Seho Kim and in collaboration with members of Tina Shaw's group, Jay Lim and Rajib Sahu. And then towards the end, I'm going to present you some of the recent work that has been performed by Emil Zoka collaboratively with Seho Kim. And all of this is underpinned by the amazing activity by Lee Stevenson, as part of the group. And some of the work from Seho that I'm going to show dates back from his master project that he did with Pyok Pa Choi at the Korean Advanced Institute for Science and Technology, and Pyok was my predecessor at MPIE. So why would we care about the analysis at the near atomic scale of nanoparticles? Like for every single other material that you can think of, the way the atoms are arranged inside of the nanoparticles will play a role on their properties. So, we want to know what is their composition individually, how the atoms are arranged inside. Is it a random solid solution, or is there partitioning with different phases forming, or surface segregation, for example? Are there residual elements, impurities that have been integrated during the synthesis, for example? And then how does this affect, for example, their catalytic properties or their plasmonic properties, for example, if we are looking at nanoparticles for optical applications? And then the way over time during service the composition evolves, and for example, how does it affect their lifetime or the evolution of their properties over time? We are definitely not the first ones to do this. There's been some amazing work done in the past decades with this beautiful example from Peter Felfer, who is now at Friedrich Alexander Universität in Nürnberg, Erlangen, but who did this work back when he was working with Gilly Kearney at the University of Sydney, where they analyzed co-shell gold silver nanoparticles. So we really need to go down to this 3D near atomic scale analysis. The issue that we're going to face is, I'm going to talk about this in the coming slides. One of the first problem is that when you have a very small object that you want to analyze with atom probe, is that, as Erwin Müller said, the specimen itself is the lens for the field microscope or the atom probe. So when you have an individual object that is a few nanometers in size, how can you turn this into a suitable ion projector, if you want? So these are examples of nanoparticles, typically in solutions, and we want to find a way to turn them into a typical atom probe specimen. So, for example, here prepared by the FIB, where we do two undercuts, lift out this bar, and then turn it into a sharp needle for atom probe tomography. There's been examples of how to do this in the literature. So, for example, back in the late 90s, they were basically depositing individual particles at the end of field emitters and then imaging this by field microscopy. A similar approach, but slightly different, by using electrophoresis, was developed by Tong Li when she was at Oxford back in the early 2010s, which led to a whole range of beautiful papers from Tong and co-workers. And then there's always a possibility to embed the nanoparticles, for example, in a matrix, with these two examples from Dieter Ischheim from Northwestern, and the work from Volker et al. From, I think, the GPM in Rouen. For Felfer's work, for example, they deposited this droplet on the edge of a silicon wafer. You can see the solution after drying left the nanoparticles behind, and then you can just do a normal lift out, turn this into a needle after a flipping process where you have the platinum carbon on one side and the silicon on the other, and then the layer in between where you have the gold-silver nanoparticles. What Seho developed jointly with Pyok Pa when he was in South Korea was a way to embed the nanoparticles in a metallic matrix, and for this they were putting the nanoparticles in a nickel-containing electrolyte, and then by applying a voltage and a suitable current, you basically electrodeposit the nickel, and the nanoparticles then are embedded within the nickel. Then you can turn this into a needle-shaped specimen and run this into the atom probe as you would do for any other specimen. Here is the cell, electrochemical cell that Seho has been developing and pushing and using and exploiting, I would say. So you can see the cell is in between these two electrodes, and the electrolyte containing the nanoparticles is this beautiful green solution right there in the center. And in that case, he was depositing on a foil of copper, and you can see here the nickel that's been electrodeposited that contains the nanoparticles of interest. When we go to the fib and look in the side view after a cut with the fib, you can see the copper substrate with all the multiple grains inside, and then this electrodeposited nickel that contains the nanoparticles, and on top is just the platinum deposited inside the fib to protect the surface. In that case, the film is about 5 to 6 microns in thickness, and you can see that the electrodeposition resulted in no major voids or empty volumes that might actually endanger the survivability of the specimen inside of the atom probe afterwards. Once the needle has been made, they image the needle inside of the TEM, and you can see from the high-angle annular dark field image here that there's this heavy atom assemblies inside of the nickel matrix, and in that case is these palladium nanoparticles that are embedded inside of the nickel matrix. And when we do the typical atom probe compositional analysis, we end up with these almost pure palladium particles. Their shape is apparently cuboidal, but there are typical issues of trajectory aberrations with the different caused by the difference in the evaporation field between the palladium and the nickel matrix. So we wanted to apply this similar approach to a range of different materials, and I'm going to talk to you about 2 or 3 today and in this video. So we looked at these hollow nanorods that are made of an assembly of titanium dioxide nanowires, because they're good photoelectrocatalysts with possible applications in fuel cells. So you can see here some beautiful TM work that was done by Jay from Tina's group. And they also did some very nice electron tomography work where you can really see that you have a hollow core, it's all empty there. So one of the challenges was to see whether we could analyze this in the atom probe, and these hollow nanorods can be partially reduced on the surface to change their electrocatalytic properties. So here is, for example, the cyclic voltammetry sweep, and you can see that the properties of the nanorods before and after the partial reduction is completely different. So here is the nickel matrix with these titanium nanorods embedded, and you can see here, for example, an example of a nanorod, and the core, the hollow core, has been filled with nickel. So that was one of our main concerns, and it seems to be okay despite the size of only a few, like below 20 nanometers or something. And then we proceeded to doing a typical lift out, shape this into an atom probe specimen, and we end up with these beautiful data sets where we have the nickel matrix and then the nanorods, sometimes small bits of them, sometimes larger chunks of them. And when we do the compositional analysis, we actually detected quite a lot of impurities beyond the titanium, the oxygen, and the nickel. The interface seems to be populated by boron, for example, and nitrogen, and we also found some sodium. And all of these things, these species segregated at the interface, might completely change and the catalytic properties, and beyond, and also stabilize the vacancies, the oxygen vacancies that are deemed to be responsible for the change in the activity of these titanium dioxide nanorods. So again, good insights from the atom probe there. We then looked at some two-dimensional materials, molybdenum disalicide, disulfide, sorry, and these had been doped with uranium, and there's discussions on the change in the structure, the way the atoms are arranged in the uranium-doped samples, and there were questions with respect to where the uranium was. Was it inside of the two-dimensional sheet, or was it segregated to the surface? And so we dispersed some of these 2D nanosheets inside of the electrolyte, and then electrodeposited it. The surface in that case doesn't form a beautiful homogeneous film, but these agglomerates of nickel. And this can be understood because the nucleation of the nickel crystals will start where we have the agglomeration of the nanosheets at the start. But when we do the cut from these regions, for example, we can see that we have these nanosheets embedded in the nickel. And so we turned some of these into an atom probe needle, and we found regions where we had signal of the molybdenum, sulfur, uranium, and again, in that case, some of the. And we can see quite clearly that we have moly and uranium being segregated at the same location, so no surface segregation of uranium that could have been possible when you dope with the uranium. We also found a range of different species that were embedded, and for example, vanadium, tungsten that are coming from the moly or the uranium precursor. But these are really typical impurities, and they're very difficult to get rid of from the metal, initial metal. And then carbon, nitrogen, boron, and so on and so forth come from the precursor, the solutions that we use. So again, good insights from the atom probe on this, which would be very, very challenging to obtain otherwise. And all of these species are going to affect the properties of the material. So we see it works. Questions pertain to what to do next. I mean, this analysis of nanoparticles is not going to go away, but are there other protocols that we can use to actually prepare the specimen? So there are interesting liquid metals at room temperature. Gallium is one of them. You can melt gallium in your hand. I don't think it's a good idea, but you can do it. And gallium has a fairly low evaporation field, though. So, but maybe in some cases it would be useful. And so we tried to make a droplet of gallium. So you just put it in a pure gallium in a beaker, and then warm this up on a hot plate, and then deposit this directly onto a typical copper clip holder from chemical. And then you end up with this gallium directly sitting on the specimen, on the stub surface. And then again, what Seho and Piok did at the time was to make an indent in the very soft gallium, and then try to drop the nanoparticles inside of this indent. And then, so I think the indent, is in the copper, and then you deposit the nanoparticles, you dry the solution, and then you can put gallium on top there, and then you can try to turn this into, again, some sort of protected environments for the particles. The thing is, the gallium melts at very low temperature, as I've said, so when you want to try and do the typical lift-out protocol, it becomes really quite tricky. It melts during the fibbing itself with gallium. And even when you manage to do it, it's difficult to turn this into a needle afterwards. Creates voids and typical melted structures, so using this as an approach seemed to be a bit difficult, let's put it this way. The guys at the University of Oxford revisited a typical approach that was tried back in about 20 years ago when fibs started to appear, where you could make a moat and then leave a pillar in the middle that you can turn into a needle, and this can be done fairly easily with the use of a plasma fib. So they published this. It was a collaboration, I believe, with the University of Glasgow, and they reported these interesting results on a titanium alloy. I think since then they've been using this quite a lot for looking at aluminium alloys, because xenon-based plasma fibs are much better to avoid typical gallium embrittlement of aluminium alloys. We tried to reproduce this, so we put gallium, liquid gallium on the stub, and then made a Death Star, and then turned this into a specimen. And all of this was done at cryo conditions, so at minus 140, minus 150 degrees, to avoid the melting, and we avoided the melting. It worked fine. Transfer this into the atom probe through a vacuum carry transport suitcase at low temperature, and we can see here the specimen inside of the atom probe, and we had no results. But it's not a lost cause. Some things there can maybe be made to work in the future. But another fairly well-known liquid at room temperature is water. So could we use ice to do this? There's been a few reports of water ice from Stefan Gerstl and the group at ETH Zurich. I think he also reported on the analysis of interesting beverages like beer. But we know how to make ice. We also know quite well how to make these beautiful Christmas trees from our atom probe specimens by leaving them at low temperature in a moist environment. And Lee and Agnieszka, Isabel tried to analyze more or less what would be seen as an icicle a few years ago. They dropped a fairly large amount of water at the end of a paper clip, and then turned this into a needle with the plasma fib after several hours on the plasma fib, and they transferred this into the atom probe, and actually never got anywhere. We never got any ion emitted from this specimen that was half a millimeter in length, and we tried up to about 11 kilovolts at the highest laser power we could go to at the time, and got nothing out of it. There's the amazing work that's been coming out of Dan Schreiber and Danny Perez's efforts to look at water-containing gels on some of these glass that are used, I think, for storage of nuclear waste. And so the trick that they did, so the equipment that they have at PNNL allows them to do cryo lift out, so the needle from the fib is actually cooled down, and so in principle, if the stage is cold, you can approach, cut with the fib, approach with the needle, which is maintained at low temperature, use the redeposition from the cuts to stick the needle onto the bar, and then do a typical lift out, and turn this piece of the material into a needle, and then do the analysis as you would. And I think the paper is now published in NPJ materials degradation, I believe. And here you have a gel that contains water and a whole range of different weird stuff. And I think this is a comparison also. There's a comparison in this paper with some molecular dynamic simulations. It all seems to match quite well. But here what we have is then a matrix, a solid matrix in which water is embedded. So based on these ideas and some discussion that we had with Julie Kearney once she was visiting MPIE, we decided to try and use an approach using a skeleton, if you wish, of metal, and in which we would put some water. And so one way to do this is to use nanoporous gold, for example. So you start with a silver gold alloy and you stick it in solution to do some partial dissolution, and mostly of the silver, and you're left behind with this network of pores of mostly gold. And so you have an interconnected network of pores, and this could actually then, if we put liquid inside, offer some sort of backbone to support the water. So that was our initial idea. And so we did this, and we put some water on a thin foil of nanoporous gold, and then use the moat-approach that comes out of the Oxford-Glasgow connection. And we were left with this gold, silver gold alloy, and then the nanoporous region, and then this small droplet of ice that we turn into a needle. And then we use the cryo vacuum transfer suitcase at low temperature to bring this into the atom probe. We used heavy water in this case, in part because we wanted to distinguish what might be coming from the chamber, from the frosting, and see, what we would get out of it. And so we get a range of different molecular ions with different number of molecules of water that are agglomerated, and they all tend to be with added protons or deuterium ions, and that might just be coming from the conductivity in the ice has to be ensured by protons. So there might be some protons that are being ripped off from the water as we form the ions. This raises a lot of questions and interrogations on how things work, but this is going to come later. We put together a paper on this, which should appear early December 2020. The group at Stuttgart has results that are very comparable to ours, which is really reassuring in some ways, on also pure water and some solutions. But in principle, we could use water as a carry medium for analysis of nanoparticles. To conclude, atom probe can be used to analyze nanoparticles. There's nothing new there. It's been done for probably 20 years now. There's been a lot of examples of atom probe for looking at catalytic systems. For example, the great work coming out of the Brussels group from Norbert Cruz and Thierry Vizard de Boccarme and the people working with them over the past decades. So, there's again nothing new there. But typically for individual nanoparticles and not looking at the end of the needle as a catalyst nanoparticle, but individual particles separated, we need to embed them in a matrix. So we need to define the right matrix for the right nanoparticles. So we can use nickel, like we've done quite a lot here, to embed the nano objects or nanostructures. We could potentially also use gallium or maybe indium, some of these very low melting point metals. We've also shown now that water can potentially be used for this, for low evaporation field materials. Otherwise, the trajectory aberrations might be really bad. And we can make needles from all of these different systems by going to cryogenic temperatures. We can also do this with water, which is quite interesting. And all of this will help us push further the understanding of the property relationships between the nanoparticles composition and their properties. So I want to thank all of the people giving us money to do this amazing work. And so first and foremost, the Max Planck Institute for Eisenforschung, which has been supporting us with bringing in money for new atom probes and quite a lot of fantastic equipment. We've got support from the DFG and the CERMAT school, which is the graduate school funding some of our PhD students. There's been also funding from the BMBF to, for example, our plasma fib and some of the cryo attachments, and the European Research Council that funds quite a lot of the people who are pursuing this work. And on this, thanks for your attention, and if you need, just reach out. Cheers.